Today I will be talking about the dark art of building a production incident system. And the first question that might come up, so why should exactly I be talking about it? To give us some background, I've been working in the performance space for now about 15 years or so, mostly building actually tools. I also help customers optimize stuff, but I come from a tooling background and I'm now working for a startup that's called Ruxit. What we build a new SaaS performance monitoring and optimization solution. And obviously one key of monitoring is you have to figure out when something goes wrong. And the reason why I called this talk the dark art, because that's how it sometimes feels. People try to do certain things, they throw some math in there and do some things they found somewhere on the internet to figure out where to throw an internet or not, or they do some voodoo like if something is failing for 15 minutes and the sun is shining, but it's not above 70 degrees or whatever. And what I'd like to do is give you like an overview of kind of what it boils down to if you want to create an incident system that produces reliable incidents that you can understand. One of the questions in the comments of the meetup was whether I'm covering actual tools today. I won't be covering tools today of any sort. I rather want to give you an idea what you should look, what a tool should provide you with, or how a tool should be working, or kind of give you the tool set that you need to figure out whether a tool is actually doing something useful or not. I'd like to start a talk with talking about what I will not be talking about. When you talk about incidents or stuff breaking in production, there's obviously a lot of stuff that can go wrong. I won't talk about when like cables are broken. So someone plugs your internet connection and the whole data center is down. Therefore, you don't need an incident management system. You'll figure it out. You might even hear it, or kind of everybody will be upset and so forth. The same is true for other incidents that can happen in your data center, like if your data center is on fire. There are pretty super incident management systems that have nothing to do with software at all. But when things go wrong, it's typically not always a fire or somebody cutting the cable of your data center. It's like a lot of everyday stuff. So a lot of stuff can happen, or we do a lot of stuff to our environments that eventually might cause us to have problems. One example is deployments to production. So you're kind of deploying new code in production. You're doing it continuously. You have multiple teams that deploy in production more or less simultaneously, not knowing that somebody else deployed something at another component in production, and suddenly something starts to break and everybody's wondering why. Or first of all, you have to kind of figure out that one of those deployments actually caused a problem. You might do an infrastructure change. So whether you're running in the cloud or you have your own data center, you decide to spin up a couple of instances, recycle some instances, change some configurations, and things might change as well that you should be notified about that this was not really a good idea. So it's a lot of everyday stuff that typically causes us problems as well. And the art is kind of figuring out whether this everyday stuff that we are doing is actually causing us a problem. And a bit more what we are actually doing, what our challenge was. So obviously building an incident system per se is hard. But when we were building it, and I told you I'm coming from a tooling background, our main challenge was scaling an incident management system. So our point is we had to build an incident system that works for over 1,000 different applications that we have no idea how they are built, and it has to work out of the box with manual configuration, and everybody must understand how it works, and obviously it should produce meaningful results. So it's not about tweaking and fine-tuning a system for your very specific purpose. It's more kind of a one-size-fits-all that really fits all and covers most of the use cases. Because obviously you can't have 1,000 people calling you, okay, how do I fine-tune and tweak certain things? So it's really about a system that learns itself and works pretty fine for most of those use cases. And today I'll kind of give you an overview of the technical underpinnings of what it actually takes to build such a system. So just to give you an idea of how it feels to do what we do, and I also have a question for you now. So this is one situation we could think of. So you have a typical error rate of 3% at about 10,000 transactions per minute. Now during the night you have 5 errors in 100 requests. So this is a 5% error rate now. This is nearly double of your usual error rate. Also your load is much slower. My question to you is, who of you would alert? Or who of you would raise an incident? Okay. Who of you wouldn't raise an incident? Who of you is not really sure whether they would or would not raise an incident? Yeah. Who of you would change your mind if I tell you it's 50 errors in 1,000 requests? Okay, another example. Your typical response time is about 300 milliseconds, and now you see a majority of response up at 600 milliseconds. Do you raise an alert? Who would not raise an alert? Who thinks I don't rather want to wake up that guy who's doing CrossFit for 2 years for a wrong alert at 3 a.m. in the morning? Yeah. So I think what you can see here is exactly why I came to this dark art. Even if you say you would or you would not do, it's like you're kind of a gut decision right now. If I would ask you why exactly you wouldn't want to do it and like give like a really deep explanation what you do and what you don't do, it's kind of hard. It's like a gut feeling. You would do it, wouldn't you do it? And it's a case-by-case decision, but we obviously have to move beyond case-by-case decision, because otherwise it will be you sitting there 24 hours getting every incident and figuring out whether you actually should create an alert or not, which is kind of counterproductive. The key point that I kind of came to, I mean, we're all engineers, right? And give us something that is broken and we will be so happy to fix it. No matter how long it takes, give us enough pizza, coffee, and Coke and we'll fix it. Huh? That's our profession, that's what we're doing. So we're really good at fixing stuff that is broken. But to be honest, we're not that good figuring out whether something is actually really broken, like in the case of alerting. Like we saw before, we were not all kind of clear on, okay, is this now an alert? Shouldn't it be an alert? And this is kind of what I figured out. So we're really good at fixing stuff, but we're not so good at detecting whether stuff is really broken. And there's actually a reason for this. And before we go for the reason, the question is, how can we actually get better at figuring out whether stuff is broken in kind of a consistent way so that we're really feeling comfortable with it? And unfortunately, the answer is not very comforting. It's all about statistics. Sorry, guys. You didn't expect this. Or probably you did. So the truth is, what we're doing here, we're dealing with a large amount of data, a large amount of numbers. And the science that deals with this is about statistics. So whoever went to college for a computer science degree, they have done some type of statistics courses. But this is a long time back, and if you were like me, you weren't especially mostly interested in those talks and still figure out how you pass the exam. And you kind of later on realize how important that stuff actually is. Just to give you a quick management summary of what statistics is actually all about. Statistics is about objectively lying to yourself. So why is this? Statistics actually always aggregates data. You're not looking at the whole data, you're looking at the representation that does not contain the whole truth. So you're deliberately leaving some stuff out so that you get an easier to kind of condensed statement for others, which is some sort of lying. It's not the worst one, but it's some sort. However, good statistics is about objectively lying to yourself in a meaningful way. So what does in a meaningful way mean? It means you understand why you're getting the results, and you know that even if it is kind of a statistical lie that you're looking at, the data still makes sense to you and you know why you're actually getting this information. So it's not just about seeing all the data, because otherwise we could always look at all the data. So we see a simplified version of the truth, leaving out some pieces, but we still can rely on the result of this lie we're telling ourselves. Now coming back to how do we actually design an incident, and if you look at it from 10,000 feet, it's actually super easy. Like what we have here, we have like some metric that we're looking at. We have a baseline and we have that metric going above the baseline. So what's so hard? So why do I spend 60 minutes talking here how about to create an incident if it's actually that simple, right? Once you look closer, there's a couple of tough questions you can ask, like which metric do you actually pick to create an incident? how do you calculate this value over there? So how do you arrive at this value? How do you get this baseline that you're looking at? And how do you actually define that this happened? So the more you look at it and at the detailed level, you figure out it's a bit harder than it looks in the beginning. First, start with metrics. Which metrics do we want to pick? The beauty about metrics is that there is so many to choose from, and we can look at many of them. And for the purpose of incident management and alerting, I categorize them into 3 buckets. The first one are capacity metrics. They more or less define how much of a certain resource we are using. CPU utilization, memory utilization, connection pool usage, these kind of metrics. So it's more or less a percentage of whatever is available that we're looking at. The second metric that we're looking at is our discrete metrics. Discrete metrics are simple countable things. Number of users, number of errors, these kind of things. So the nature of discrete metrics is if you pick a certain time interval and you look at that metric, you can arrive at a single value. So there's not multiple value for a certain interval. If you just make your interval small enough, like your measurement interval is a minute, and you look at users per minute, there is a value for users per minute. There's not 10 or 15 values for users per minute. And then we have continuous metrics. So metrics that kind of represent a range of values at any given point in time. The point there is you can make your observation window smaller and smaller and smaller, but you will never arrive at a single value. You'll always have a range of values. So which of those metrics do we now pick for alerting, or how well are they suited for alerting an incident? Capacity metrics. And this is my perspective. Capacity metrics are good for what the name says. They're good for capacity planning, but they're not so good for production alerting. The reason is, let me give you a couple of examples here. Looking at connection pools. I've worked with a lot of people setting up monitoring system, and very often the questions come up, shouldn't we create an incident if our connection pool is used 90% over 5 minutes? And I asked them, why? You made it that big, it's supposed to be used, right? So why would you alert on a 90% usage of a pool? It would be actually much better to alert if you look at a connection pool on a connection acquisition time. So can I get something when I actually want it, rather than how many of it is currently used? It's the same with a lot of resources. They are there to be used. That's what capacity planning is about. We should have the resources that we use, but we shouldn't have so plenty of them that we're not using them at all. This would just be running way over capacity. And in the case of connection pools, the acquisition time is much more representative for whether we have a problem or not, because it tells us, do we get what we want at the time we want to get it? So you can run at a 99% connection pool usage, and your connection acquisition time is about 0 milliseconds or close to 0 milliseconds, so everything is fine. You can be at 70%, and some of your transactions have to wait 2 seconds or longer for a connection. So connection acquisition time tells us whether anyone needing a connection actually gets one. Another example is CPU usage. You still see people alerting on high CPU usage. And there's long threads on, is it 95%? Is it 99%? Does it depend on how many cores I'm actually having on the system? And these kind of things. I think for really raising an incident, CPU usage is not really good. It's indicating the health of your system. But you shouldn't ever raise an alert just because of CPU usage. And before actually going for CPU usage, it's much better to go for a combination of the load average and CPU usage, actually telling you, again, as in the connection pool example, did everybody who wanted to get a certain resource actually get that resource? If you want to be even smarter, you can correlate it with response time so that you can actually figure out whether your shortage of CPU is actually causing any response time problems or not, because that's when you're really having a problem. That's when you really have to look into an incident, because even if your system is kind of running very much at its limits, or maybe slightly above that limit, and your response times still all look fine, it's not the best reason to wake somebody up at 3 a.m. in the morning. So my point is, I wouldn't actually use these metrics for alerting. They're good for capacity planning, they're good for understanding the health of your system, but you should not really raise an incident based on these metrics. With discrete metrics, I don't want to spend a lot of time on those. They're pretty easy to track and analyze. Typically, you don't really use them for a lot of incident management alerting anyways. With continuous metrics, they are kind of the toughest metrics that you can work with. Simply because they require some extra work, because they're not that easy to track. You don't get this single value, you always get a range of values. And you first have to figure out which value you actually want to work with if you have this big variety of metrics. So the big hope would be that your chart of response time might look something like this. It's like a single line over time, and you have a value, like this case 42, and you know exactly what the response time is. Unfortunately, this is what the reality of a response time distribution looks like. As you can see here, and now I actually have to stand up, so some workout. You see it's always spread across a certain range, and you have some outliers over here, some outliers here, some outliers here, some outliers here, and also others over there. And now we have to come up with a way to represent this in a single number. So this is what the average would tell us about those metrics. And if we look at the average, we see a couple of outliers. So if you would look at that metric from an average perspective, there's one at the very left here, one here, one here. So this might result in actually 3 alerts, and 2 of them kind of are coincidental with the outliers here, more or less. But overall, you see the average here is not necessarily the best representation for a response time. And this here at velocity, so Sergey mentioned velocity, I think there's now this common understanding that averages are not a good way to represent response times. This is what the median would tell you about the same metrics. What you can see, the median would only see one change, which is here, compared to 3 that are here. And you can also see, switching this back and forth, that the point in time where the median alerts, the average wouldn't even alert. So changing your data representation has a direct impact on which value you're looking at and whether you're going to alert or not. So for our metrics, we first have to choose a representation that's pretty close to our data. And obviously, we've seen that the average is much more noisy here. And the median in this case is a much better representation. But even if we have this value now, we need to calculate a baseline. So what's our normal response time? The hard thing to realize is a baseline, also it's very often drawn as a line. A baseline is not a single number. It's not that easy that your baseline is 300 milliseconds, 400 milliseconds. A baseline is actually a range of values with an associated probability of these values to occur. And that's now where statistics comes into the play. The most widely known form of a distribution model is normal distribution as a baseline. Whether you agree to use it or not, it's just a good example to see what we're actually talking about when I say baseline is not a single value, it's a range of values plus probabilities. Our mean in this case is 500 milliseconds, and we have a standard deviation of 100 milliseconds. What this tells us is that 68% of our response times are between 400 and 600 milliseconds. 95% of our response times are between 300 and 700 milliseconds. And 99% of our response times are between 200 milliseconds and 800 milliseconds. That's what a baseline distribution actually looks like. However, if you use the wrong distribution model, and that's one thing you should really learn, that I really remember from my statistics courses, if you pick the wrong distribution model, every observation you try to describe with this distribution model is actually wrong as well and very much misleading. Like in this case, you see an example of a base response time of 140 milliseconds with a baseline standard deviation of 959 milliseconds. So in this case, the idea was we have response times, they have a normal distribution model, and this is our baseline response time, and that's our standard deviation. Just to make it bigger, what the conclusion was. So kind of 2 to everything between 2 times the standard deviation is fine. So for a response time that is 140 milliseconds, everything up to 2 seconds is fine. Everything up to 3 seconds is kind of a warning, but everything over 3 seconds is definitely a problem for a typical response time of 140 milliseconds. If you actually think back what we talked about the slide before about distribution, this would actually mean that within 1 standard deviation, there's actually negative response times. So unless we're really using a quantum computer here, this is not even possible. So what happened here, you kind of forced a normal distribution on data that is not normally distributed, predicting how the data should behave. And the result was a system telling you that if your response times that are normally 140 milliseconds are about 3 seconds right now, you're really having a problem. I wouldn't need an incident management to tell me this, right? Funnily, this whole article was published under Why Alerts Suck and Monitoring Solutions Need to Get Better. It's kind of a funny title for this here. But I think you get the point here. By the way, what every monitoring system should do, you cannot just look at a distribution model, but there are also statistical approaches where you can verify that your data actually follows a certain distribution model. So if you say, this is my data, I assume it is normally distributed, you can test whether the data is actually really normally distributed. So what's the result of doing something like this? The result of this is that you're getting false alerts. So now looking at the average again, and we take this very aggressive baseline of more or less 1 standard deviation, we are creating 1, 2, 3 alerts. If we think then, that's what's sometimes happening, no, we are not taking 1 standard deviation, that's creating too much. Maybe we go with 2 standard deviations, or 3, or whatever. So what you see happening right now, we're not getting any more alerts. Obviously the false alerts are now gone, but there are no alerts at all. However, what we have to do in the end, we now have to find the right distribution model, because otherwise we cannot kind of pick our baseline. If the distribution model is wrong, we either get too many or no alerts at all. The thing of picking the right distribution model is that it can be very hard to impossible given the data that you have. If you Google it, you will find people saying, yes, it's a log normal distribution. Others will say it's this type of distribution, it's this type of distribution. The truth is, your distribution model might look like this, which is probably a log normal distribution, but doesn't necessarily need to be one. Or your data might look like this. So what do you do now? Or it might just look completely different. Actually, you never know, and some people say they can look at a distribution model chart and they exactly know what the underlying distribution model is. This is like really black magic, because even statisticians can't do it. That's why they invented methods to actually test whether they can do it or not. And I can show you some distribution models that you think might be normal distributed, but they're not, and other examples as well. So how can we solve this problem? So obviously we need to understand the distribution of our model to define a baseline, but we can't figure it out. That sounds to be like a serious problem that we have to face. To get an answer, let's look at the normal distribution again. As you can see here, this is like the distribution ranges, like the probability ranges for values to occur. The same example we had before, just now with just the probabilities in there. What you realize if you look closer is that 50% in a normal distribution are slower than the mean. That's what the normal distribution more or less says. This is what we call the median. 97.6% are slower than the mean plus 2 times the standard deviation. So that was kind of the 2 times standard deviation we wanted to use for alerting. This is the 97, so 98th percentile. So we can also get the same information by using our data. And I've talked to a lot of people say, what do you use for monitoring? They say median and 98th percentile. And when you ask them, why do you take the 98th and not the 95th or whatever, I said, yeah, 98 sounds kind of good. So we went with 98 and it sounds kind of reasonable. So there is a mathematical reason why to go with the 98th percentile. And it's just 2 times the standard deviation of the median in a normal distribution scenario. But this also tells us something else. if we look at the 50s, the 90s or 98th percentile, to define normal behavior, we don't need to worry about the distribution model anymore, because we can always calculate the median and any percentile value which we actually want to get. So we can do it on any type of data. We will always get these metrics, and we don't need to care really about the underlying distribution model in the data. And in this case, this is what then happens. This is just an alert on like your regular response time, your median response time, and looking at the median and the alert. In this case, the alert really triggers at the right time, when you're really having a problem, when you really see abnormal behavior in your data, following the median. And obviously you could do the same for a 98th percentile for your slow request. So now we have defined normal behavior. So we have like the 50s and the 90s something percentile. But how do we now define non-normal behavior? So does this now mean when our median is over our baseline median, we have to alert? And when our current 98th percentile is our historical 98th percentile, we have to alert? Is it this what we have to do, or do we have to do something more kind of fancy, like when it's 3 times over, 4 times over, whatever? Fortunately, this is not the problem we need to solve. All this is about it's not about defining non-normal behavior, but what statisticians are talking about is about expectations and whether a certain distribution model fulfills an expectation that we have right now or not. And we have a very clear expectation right now. 50% of our data in that range, 98% of our data in that range. And we'll now look at 2 scenarios. We look at the scenarios we had in the beginning. So the expectations, or the questions we're asking ourselves, is a certain error rate likely to happen or not? Or is a certain increase in response time significant enough to trigger an incident or not? We again take the example from the beginning. We have a typical error rate of 3% at 10,000 transactions. During the night, we now have those 5 errors in 100 requests. Should we alert or not? And this question actually brings us to Las Vegas. Why do you think this brings us to Vegas? Exactly. And Vegas has to do a lot with probability. So how likely is it that you win or lose? And in fact, a lot of the mathematicians in the last centuries, they were pretty rich. They would like to gamble, and probably the reason why they like to gamble and obviously they wanted to stay rich and not lose their money is why they started to do statistics in the beginning. So a lot of statistics is actually related to probability and how likely it is for a certain event to occur. And once you start doing it, you kind of figure out statistics is kind of everywhere. Like, how likely is it to see the 4 and the 5 of these 2 dices in exactly the order, the left being the 4, the right being the 5? How much likely is it to have a 4 and a 5 and the order does not matter? So this is all about probability, this is all about statistics. And there's a very simple distribution model that we can do this, that we can use, which is the binomial distribution that tells us how likely it is to have n successes in a certain number of trials. That's more or less the mathematical definition. So how likely is it to get exactly a 4 and a 5 rolling 2 dices 10 times? Just rephrase the question. How likely is it to get our 5 errors in 100 requests? And what we do is we simply draw this probability curve here. So showing you how likely it is to get 5 or less errors in 100 transactions. And what we come up with, we have an 18% probability to see 5 or more errors, 18% probability to see 5 or more errors. This is way in the band of 2 times the standard deviations that we were talking about. So in this case, we do not need to alert, because in a small data set, this is what's likely to happen. And as a matter of fact, most alerting systems have problems when there's a low number of requests on a system. They don't have problems if there's high load constant load with nicely distributed data. Typically, when your amount of load goes down, they alert too early, not when your load is extremely high, unless you really have obviously a problem and overload your system, but that's another story here. So now we cannot just say, yeah, I kind of have the feeling that 5 errors in 100 transactions might be okay. You can say, actually, that's pretty likely to happen. So how do we handle this now with response times? And I have taken a very small sample here. Obviously, even if you look at a smaller time interval, this might be hundreds of thousands of values, but they don't fit on the slide, and I think it's still good enough to make the point. Our median response time is 300 milliseconds, and we measure 200 milliseconds, 400, 350, 200, 600, 500, and so forth. So a lot of values that are actually above 300 milliseconds. And it's more than 5 values that are above this. So how do we now handle this problem? That's obviously a bit different than the error problem we had in the beginning. Unless we use an approach that I refer to as percentile drift detection. The idea behind percentile drift detection is obviously when you look at 2 different time intervals and you look at any percentile, whether it's the median or the 98th percentile, they will never be perfectly equal. They will always be slightly different. So reaching exactly the same number is impossible. The question we have to answer now is how far can they drift apart, which is still okay. So when are they drifting apart too far? So when are the percentiles drifting afar too much? And the idea is really detect those drifts and figure out how big those drifts actually are and when they become significant enough. The good thing about this, this is again pretty easy to calculate. So but first of what you have to do, we have to figure out all the values that are above the median. And in this case, it's 7 values that are higher than median, and the question is this normal? This question is again the same questions that we had before with error rates. How likely is it within 10 values that 7 values are above the median? So normally it's 50%, and we in this case can again use the binomial distribution to answer this question. We have a 50% likeliness to see values above the median. How likely is it to see 7 out of 10 samples that they're actually higher than the median? And the probability here again is about 17%, so we should not alert. So for this small load, this is also perfectly fine. So what we more or less did, just to recap from the beginning, we totally dropped figuring out a distribution model because we simply said we don't need it. We just switched to the median and the 98th percentile. And then we switched to a very simple distribution model that's just telling us the probability once we look at 2 values, how far those values drift from each other and how likely this is to happen. And by doing this, we created a very robust incident management system that will work well under high load and under low load, and it's also easy for people to understand why the system actually works that way. So as you have seen the statistics behind it, that's not rocket science. That's something you can explain to everybody late at night with a beer, and they still figure out how it works. So the good news is now we're done. So we have defined which metrics to pick. We talked about how we get our baseline. We now defined how we kind of figure out that you have the baseline violation. And obviously we also have talked how to actually define our monitoring values. So at the end of the talk, people normally get super excited and want to go home and build their own incident management systems and don't want to sleep anymore. Just a word of warning. This was just the beginning. Obviously there's way more complexity once you look into the nitty-gritty details of building those systems. I wouldn't recommend anybody just to build your own ones. There are lots of tools out there that allow you to do the statistics, like the example that I've used before, like with the probability. I used a very advanced monitoring system, which I call Microsoft Excel. Obviously, you can make it part of your monitoring system, but the algorithms used here are pretty widely available in statistics tools. So once you dive deeper, there's obviously way more complicated mechanisms to do those things. There's way more advanced ways to check for statistical relevance of 2 values and so forth. So if you go to Wikipedia, you will find Wikipedia pages that are full of mathematical formulas that actually wouldn't even fit on the screen here, and there wouldn't be any value in actually showing them, because the basic idea and the basic underpinnings are pretty much the same. They are just tailored to specific use cases more than this, but the principle kind of like always stays the same than we are using here. And the key takeaway should be, when you have a monitoring system in place that creates incidents, or somebody wants to convince you that you should switch to this system because this is like really great and it can do all this monitoring and figures out everything perfectly, just now you should know asking exactly those questions. So how do they actually get measures? How do they define baselines? How do they get to validations of baselines? Which metrics can those systems actually work with? And if somebody starts to talk about normal distribution and other weird things, you know, it might not be the systems that you're actually likely to choose. Okay, with this I'm at the end of my talk. You can find the slides right there at bit.ly, New York City WebPerf. There's one Earth too much in there. It should just be one. You can also ask me on Twitter, and just a very small advertisement. We are currently a startup in early adopter mode. If you want to try out any of those algorithms, we have an early adopter program. It's free to use. If you want to try it out, give it a chance. And now I'm open to questions. So the question is whether it's worse when you drop below, not just above, because we were always talking about going above expectations and going below expectations. So statistically, it kind of is relevant, but for errors, we don't alert if errors go below a certain value. We have the information, but people actually wouldn't really know what to do with it. However, you would do it right, because the most likely reason why your response times drop significantly is because you start to ship different content, or something is really broken. But you also should see this in typically request count. So we do this for requests. If like the number of requests significantly drops below a certain expectations, we would create an alert, and that's how availability, for example, with real user monitoring data is often done. So we don't do it because we say, well, what should we tell you? Your error rates are lower than ever before. Would you really want to wake somebody up right now? I mean, I can see the point. It might just be that your page is returning nothing, but that's then more about the monitoring system that you're using. Either your monitoring system is broken or your application really got better. But we decided not to alert on error rates getting actually too low. Yeah, so I'm not implying that you actually should use normal distribution here. So the point I was trying to make, a lot of tools are actually using still normal distribution. My point was they're not actually using normal distribution. They are looking at the 98th percentile for defining abnormal behavior, or the median for normal behavior. And you don't need this to imply the distribution model on the data. You can just work with the actual values, which is the median and the 98th percentile. That there's other behavior in your system that might suddenly change, and something is broken, I agree. And then I have worked with a lot of performance teams who know their applications pretty well, and they know they can create alerts on certain application problems that is very specific to their application. Like I know one really big company, they really know when their available thread count on their front end goes above 15, they have a problem. And should you be able to alert on those things if you really have that domain knowledge? I think it's fine to alert on those things because you have learned it over time that this is really creating a problem because the way your application is structured. The point is, I was trying, how do you do it if you don't have specific domain knowledge and you want to get a system working? Then you can't rely on these things. So the approach that we are going is we're building like the overall things that we know will work in any case, maybe missing out those cases immediately, but typically you would see all the other behavior failing as well. Should you still be able to do this very domain-specific alerts? Yes, I think you should. But you should really know your application well enough that it's really worse than really raising an operational alert if this happens. So I'm not saying you shouldn't, but obviously you know your application well enough. But you couldn't say to like somebody else working at another company, if your memory usage drops to 50%, you should raise an alert, because for them this might be actually normal behavior of a very big JVM doing garbage collection and another cluster is taking over for that time period, for example. So it might make sense in specific cases, but I'm more concerned about like what you can generally do without actually having that specific context of an application. That's a very good question. What's the time window? And that's actually the point I deliberately left out of it. What the time window is. And we are actually working with dynamic time windows. So we are more or less turning the distribution model upside down and taking, okay, how big must the time window be to have enough significant data to actually calculate even the current value on? Because the current value in any application, like response time this minute, is pretty useless if it's just 3 or 4 requests, especially in low load systems. They don't really matter. So what we do, we look at how many data do we need to not have like this big significant jump if one value is out of bound or not out of bound. And so therefore we adjust it. So in high load scenarios, it might just be minutes that we're looking at. And in low load scenarios, that window might actually stretch out to be longer than this. And for the baseline, if that was the question, second the timer for the baseline. So most of the applications we look at, what I've kind of relearned, when people often say you have spikes in response times under high load, what we've seen way more often, you have spikes in response times under low load. Most systems are defined to run pretty well when there's load on the system. And actually, even if you stretch the time window out, you will see that statistically less is changing that you might actually think on your 95th and median percentile. So we typically take much longer time ranges on the baseline values that we're looking at. And the data, actually those spikes don't get factored in as much as you would actually think they would. And that's also something we had to learn, because when we initially started, we had this assumption that under very high load, you have those very high response times. This was never the case on a well-tuned system that we actually looked at. This has never happened. So we typically work with a baseline window of about 7 days and look at the data within those 7 days, but also do noisiness checks, whether it actually makes sense to create reasonable baselines or not. The only downside of using this approach, this is a question that sometimes comes to this one as a follow-up question. If your system is very slowly degrading in performance, like over a month, you wouldn't see it with this baselining approach. Yes, that's true. You wouldn't see it with any baselining approach. But this is not the problem of an incident. This is not something that suddenly changed. This is just you suddenly writing slower and slower code, and an incident system wouldn't react on this. This is something you, for situations like this, you should actually do like regular performance checkups of your application with your ops and architect team anyways. But that's not what an incident system from my point of view, is built for, to show these slow degradations over months, because they can also be natural. If they really hit the hard boundary, that's what you have an SLA for. Yeah, so the question on queues, so how do you handle queues? Because like they sometimes really fill up and then slow down again. It might be that something crashes, or it's just a problem with the queue and so forth. Queues are hard. So what we do, we still, I mean, there might be statistical approaches, but we actually changed the problem to be different. We still look at overall processing times. So it really depends on how you measure it. If you just look at the queue, it's kind of hard. Obviously, measuring a queue response time doesn't make any sense, because typically it's super fast to put stuff in a queue, even if it doesn't get processed. And obviously, obviously there's something like a drop rate on a queue. You should never have drops on a queue. That's an obvious one you would alert on. That's maybe only one of the few capacity metrics you actually really want to alert on, because if like your queuing system start to drop data because they can't process it anymore, then you would alert on it. But if you really look at queue throughput, that might be a much better metric to look at actually. So it's more a question of metric than the statistical model. It's whether it's queue throughput and it's overall queue response time. So sometimes you do the instrumentation and you code on the monitoring level. So how long does it take until you get that value back, or how long does it take until the overall request is processed? Because that's where it will manifest first when you have a problem or not. So that's why, because queues by their very nature are a bit harder to handle here. No, we haven't. We went more like for the overall transaction response time, because we have the possibility to actually trace through a queue. We rather focused on building this into the system than looking at queues specifically. But there would be like different approaches. But the one for response time, and the reason why we also went for those, and that's I think generally true for a lot of those approaches, why we rather stick to simple, very simple mathematical approaches, because you can also do this with self-learning and so forth. The problem is that somebody at the end of the day has to understand what's going on there. And this is like, it now takes you longer to process. So normally they have an overall processing time of 300 milliseconds. Now it's 400, 500 milliseconds. And it's for 60, 90% of requests. It's much easier for people to understand than to tell them how it's like statistics kind of worked out. I'm not saying that you can't do it, but we try to keep it to simple metrics as much as possible, because it's easier for people to understand how they should actually react on those. I have people, for example, seen also using something like self-learning algorithm, but what does it tell you if node X17 has now a weight of 0.8 and should have 0.6? So what's broken? So the question was more or less, if something is slowly degrading, when will you eventually reach a point where your system is most likely to break? And the point was looking into predictive analysis. Predictive analysis tool things when stuff going to break. And response time is one example, but another very prominent example is disk space. If your disk kind of gets used up over time, you don't want to see that you have 99% disk usage, but when is your disk actually going out of disk space? There are algorithms there. There are also predictive analytics solutions out there. There are also predictive analytics solutions for monitoring out there. I'm more, from my background, I know a couple of them. They are typically very, very expensive, because these people know that they are building stuff. That kind of makes that especially larger companies buy. And the problem I have with a lot of predictive analytics approaches is that they're very often contextless. So they're predictive analytics solutions that I know. They're really predictive analytics solutions. They're not monitoring solutions, so they don't have any domain knowledge on that data. So we are looking in it as well, but like building in additional know-how you would have like for specific metrics like a disk. You can do predictive analytics on a disk, but if you also know that your disk builds up over the day, and then suddenly a cleanup job runs and cleans it up, you might still end up having like regular alerts. But for these kind of things, you are in the predictive mode, but that also brings you, I think, away from incident management, more into capacity planning, into the capacity planning area, when will they actually run out of resources if you continue to do what you're actually doing. So that's where I rather see the predictive pieces. Because one downside of predictive analytics that we have seen is that predictive analytics tools are very good in cases where they really can predict the system, just as the name says. That sounds more funny than it actually is. I'll just give you one example where it would totally fail. Assume that you kind of certainly shift over load from one data center, or you have two data centers, and you shift all load to one data center for some reason, because one data center is down, you need to do an upgrade, whatever. So many predictive analytics tools will say, what I'm seeing right now totally freaks me out. This shouldn't happen at all. So that's why I think predictive analytics for alerting is not good, but would rather use it in a capacity planning scenario. And the one where something is slowly getting slower, I see it also rather as a capacity planning issue. And those algorithms definitely have a value. So the question was, he's looking at incident management tools. What are kind of the red flags? What tools should not be doing, or what kind of... Actually, that's already the first thing. An incident management tool, to the point of alerting, shouldn't you require to learn a lot and do a lot of configuration. They should have the kind of the mathematical tool set built in to figure out what the tool is doing. So if a tool, that would be one example, tells you, you kind of have to define a threshold, or you can do something like, should there be 3 or 5 violations when you alert, when you de-alert? This is for me a red flag, because how should you ever know? How should you ever define this for 10,000 or more metrics? Like to that question before, if you have really one domain-specific alert, it might make sense to define it. But for the general purpose, if you have to configure and define a lot yourself, that's for me definitely a red flag. Because you will never get it right. Nobody ever will, because you would actually have to do what those algorithms do. That's definitely a red flag for me. What would also be a red flag if I actually don't understand how they work. Not the very details, but at least some mathematical underpinnings, like the statistics that I showed you here. If you can figure it out, then I would really be worried. And if they would use something like a normal distribution in there, or if nobody can really actually explain you how they are alerting. Because that creates a problem, that creates even a bigger problem. You can have a tool that might not be perfect, but at least you know why it's alerting. If it's like, oh, we're kind of using these 3 algorithms and then somehow weighting them, at the end of the day, there will be an engineer who has to fix the problem. Can you, with the output of that tool, explain to somebody what they actually have to fix? This is one thing what I generally also don't like, really raising an incident unless you really know what you're doing for like something like CPU issues or just for saturation issues, except in cases where you're really sure that this is something. If they don't look at something like response times, error rates in your application, these kind of things, more like the user-facing or pieces, and can alert on those, then I definitely see a red flag. But typically you will also realize, put the tool on some of your system, one of your system, give it a day of time, like it needs some time to learn, and then just start looking at the alerts it's throwing out and look at how these alerts are doing, whether they make sense to you, whether they're actual problems or not. And if somebody then comes back to you and says you haven't configured it yet, should figure out how to do that stuff. I mean, that's what you bought it for. It's like if you would sell you a car and say, yeah, but you have to kind of still run yourself. You have the car, but you kind of have to figure out how to get from A to B. That would be like, at the current stage we are at with incident management and alerting tools, there are enough tools out there that are self-configuring that can actually do this. If they can't, then it's wrong. And really to initially try to look at the data, like in the example I gave. Negative response times, seriously? Or alerts where I think, okay, this doesn't make any sense to me. But my best advice is really throw them into your system, don't do any configuration at all, and see how they behave over 2 or 3 days. So the question is, what if you if you cannot measure what you want to measure, and if you can get the metrics that those metrics? I think there's always the top 3 metrics that you kind of will always be confronted with, which is availability, functionality, and performance, more or less in the order. And if you have those 3 metrics, you are typically pretty fine. If you know that your system's available, that's great, because then users can use it. If it's not producing errors or more errors than you usually see in your system, that's great. And then you look really at response times. Then you can kind of, but that's already then becoming an art, and that's nothing you will ever get out of the box. Combine this with unusual user behavior. To give you one example, that's also where you kind of like take, for example, usage data into account. Assume you have a web shop and all your other data looks fine, but suddenly people at the confirmation page drop out. You might normally have a dropout along your money train at the confirmation page that's close to 0%. Because why would I drop out if I have filled out my address, if I have entered my credit card, if I have selected my plan? So why would I really drop out of that application right now? And then I would rather look at unusual behavior at certain points that are typically also your conversion goals, where people typically don't drop out. Because that might mean you might have missed something else in your metrics. Obviously, it doesn't need to be performance related. It might just be, or it might be like on a wider scope performance related, like a third-party CSS didn't load and the whole screen was white and nobody figured out where to click on that screen, these kind of things. Or it might just really that somebody ruined something on that page on another scale. So there I really look at, first of all, we only do it along the money trail, and we look at actions that users typically have to take. And if there's an unusually low rate of success for those actions, then typically something is wrong. It might be performance related, but it might also be related to the application. That's where then look, did somebody deploy something? Does it now look different? Is it just happening on one browser? But that's when you typically also leave this very safe place of it's more or less clear to look at your system's data to tell you what's going on. This then becomes more an ad hoc analysis, also going beyond performance. The question was on resources I can recommend. Obviously, there's a lot on statistics. If you really want to dive into the statistics piece of it, my point is that generally don't really recommend diving into the statistics because you actually shouldn't have to. But honestly, if you just go a lot reading a lot of DevOps blogs, go to Ets's blog, look at what you have on Velocity. There was the book there, Complete Web Monitoring. Complete Web Monitoring is a great book because it's really doing what it says it does. It is really complete about everything. It covers from the marketing piece to the performance piece to a lot of other pieces that you might actually want to look at. So it's not something you read in a day. The book is like this. But it's really good and complete. So if you just want to dive into those details, I would definitely go there to kind of get like a complete understanding when you build up an enterprise-wide monitoring. It also goes beyond the scope of performance.